Okay, in this lecture, we'll continue with our section 2.5 material on physical applications of the integral. And in our last lecture, we had introduced the concept of work and derived a formula for the work done by a variable force. So in this next lecture, we'll consider how to apply that work done by a variable force formula to determine the work done in stretching a spring. So the next couple of problems that we'll look at, I'll refer to as spring problems. And before we look at some examples, we need to introduce a law from physics. So in physics, a law known as Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So that is the force needed to hold a spring stretched x units beyond its normal length, which I will call f of x, is proportional to x. So that means it is a constant multiple of x, where k is some positive constant called the spring constant or the stiffness of the spring. And of course, this sort of makes sense intuitively. If we think about stretching a spring or holding it stretched at some length, we know that the further that we would stretch our spring, the more force would be required to hold it there at that length. And of course, the type of spring that we're working with will have some effect on the force required to hold it stretched to a given length. If we have a relatively weak spring, maybe something like a slinky, it doesn't take much effort to stretch it out to a great distance, as opposed to if we're working with maybe the shocks on a car, it would require a much greater force to stretch that spring. So depending on what spring we're working with, we'll have a different spring constant or stiffness of that spring, which is this constant of proportionality K. So here, a little visualization. We could think about if we have some board and we attach a spring to it at one end, and it has a natural length if we impose some force and we stretch our spring past its natural length, so let's say we stretch this thing out and we stretch it a distance of x units, maybe inches or feet, meters, whatever we're happening to use, the force required to hold our spring stretch that distance would be given by this forcing function k times x. So when we're working with these spring problems, or any time that you see a spring problem show up on the homework or maybe exams, the first thing that you want to write down is this formula for Hooke's law. In almost all of these problems, we will first need to determine what is the stiffness k, or the spring constant k. And once we have that spring constant, we have our forcing function and we can answer questions about work and other things. So let's look at an example of this. Here, we're told that we have a spring which has a natural length of 10 centimeters and a force of 40 newtons is required to hold the spring stretched to a length of 15 centimeters. So we ask how much work is done in stretching this spring from a length of 15 centimeters to 18 centimeters. So here we're asking a question about how much work is done on a spring in stretching it a given length. So in order to answer that, well, we need to know what is our forcing function, f of x, in order to hold the spring stretched to a given length. And to find that, we're going to make use of Hooke's law. So as soon as I see that this problem involves a spring, my first step is going to be to make use of Hooke's law. So let me say by Hooke's law, the force F of x required to hold our spring stretched x units beyond its natural length is proportional to x. That is, at some constant k times x. Now, to find that spring constant, or that stiffness, k, we're going to use some information that we were given in the problem. So we were told that a force of 40 newtons is required to hold this spring stretched to a length of 15 centimeters, and its natural length was 10 centimeters. So something to be a little bit careful of here when we're thinking about our answer at the end of this problem. The quantity we're interested in is work. So if force is being measured in newtons, then we would want our distance to be measured in meters, so that our unit for work would be Newton meters or joules. So keeping that in mind, since my force was measured in newtons, here my distance was given in centimeters, but I need to convert to meters. So let's think about how we can use this information. So I was given the magnitude of the force required to hold this spring stretch to a given length. So that 40 Newton force is going to be this f of x expression on the left-hand side of our equation. And that is equal to some constant k times x, where x is the distance this spring has been stretched beyond its natural length. So here we were told that we stretch this spring to a length of 15 centimeters, which would be 0.15 meters. And then we will subtract its natural length to get the length that we've stretched it beyond that natural length. Now its natural length was 10 centimeters or 0.1 meters. So the total distance that we've stretched our spring past its natural length would be 5 centimeters or 0.05 meters. That has to equal this 40 Newton force. So to solve for k, well, we would divide both sides by 0.05. So we have k is 40 newtons divided by our 0.05 meters. So let's see what this gives us. This would be 800 newtons per meter for the stiffness of our spring. So what we have is the forcing function, or the force f of x, in order to hold a spring stretched a given distance would be 800, which was our spring constant, times x. So once we have our force function, f of x, we can find the work done by this variable force in stretching a spring some length by using our work done by a variable force theorem. So here the work done by this variable force would be the integral of this forcing function, 800x dx. And let's think about what interval we're stretching over, or that we're integrating over. So here we were asked about stretching this spring from 15 centimeters, which would be 5 centimeters or 0.05 meters, past its equilibrium, to 18 centimeters, which would be 8 centimeters or 0.08 meters, past its equilibrium. So since I'm measuring everything in meters, my lower limit of integration will be the 0.05 meters, and my upper limit will be 0.08 meters. So since this spring had a natural length of 10 centimeters, when we move from 15 to 18, we're moving 5 centimeters to 8 centimeters past the natural length, which is what x represents, the distance past the natural length of this spring. So let's see what we have here. Finding our antiderivative would be, we would have 400x squared, and then we're integrating from 0.05 to 0.08. So here we would have our constant 400 times 0.08 squared, which would be 0.0064, minus the 0.05 squared, which would be 0.0025. So let's see what we're left with. So here, after simplifying, we're left with 1.56. And let's think about what our unit for work would be here. So force was being measured in newtons, and our distance, we converted everything to meters. So we would have Newton meters for the unit of work, or if you prefer, 1.56 joules would also be the same unit. Okay. So let's look at another spring problem. So in this next example, we're told the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds. So how much work is needed to stretch it 9 inches beyond its natural length? So again, what I'm given is some problem involving stretching a spring. So as soon as I see that, I'm going to write down Hooke's law. So anytime that I see I've got some problem involving a spring, I know that the force needed to stretch this spring is governed by Hooke's law, which says that that force, F of x, is given by K times x, where x represents the distance stretched past the natural length, and F of x is the force needed to hold it stretched that distance. Now, what we're given in this problem is slightly different from what we were given in the last problem. So in our last example, we were given the force needed to stretch a spring a given distance. Here, we're given the work required to stretch a spring 1 foot beyond its natural length, was this 12 foot-pounds. So what we're given here is work, not force. So let's think about how we find the work done by this variable force, F of x. So using our work done by a variable force formula, this work is given by the integral of our force function, which was K times x with respect to x, over what interval here? So we were given that we were stretching this spring 1 foot beyond its natural length. So starting at its natural length, we would have stretched it 0 feet beyond its normal length, up to a distance of 1 foot beyond its natural length. And here, since work was given measured in foot-pounds, our unit for force will be in pounds, our unit for length will be in feet. So this 1 foot would give us an x value of just 1 here. So let's see what we have. We were given that that work was 12 foot-pounds. So our left-hand side of this equation, which is work, is 12 foot-pounds. That's equal to the integral of kx from 0 to 1. So the antiderivative of this would be k times 1/2 x squared, evaluating from 0 to 1. So let's see what we have here. We would have k over 2 times 1 squared minus 0 squared, or k over 2. All right. is equal to this 12 foot-pounds. So solving for K, K would be equal to 2 times 12, or 24. And so, by Hooke's law, the force required to hold a spring stretched x feet beyond its natural length would be 24 times x pounds. So the question is, how much work is needed to stretch this spring 9 inches beyond its natural length? Now here, recall that we're measuring in feet. So 9 inches, well, there's 12 inches in a foot. So this would be 9/12 or 3/4 feet. So to find the work needed to stretch our spring 3/4 of a foot beyond its natural length, we would integrate from the natural length of 0 to a 9-inch distance beyond its natural length, or 3/4 of a foot beyond its natural length, our forcing function, which was 24x integrating with respect to x. So this would give us a 12x squared, which we're evaluating from 0 to 3/4. So we would have 12 times 3/4 squared would be 9/16, minus 0 squared would be 0. So here, simplifying a little bit, well, our factor of 12/16 would be 3/4 times 9 would give us 27/4. And here, since work was measured, or since force was measured in pounds, distance in feet, this would be foot-pounds for our unit of work. So 27/4, or if you prefer as a decimal, 6.75 foot-pounds.